Hello everyone. In this session, we are going to learn about op-amp as integrator, that is operational amplifier as an integrator. At the end of this session, students will be able to describe and analyze integrator circuit using operational amplifier and its frequency response. This is the content of today's session. Let us have the basic introduction of op-amp as an integrator. The circuit in which the output voltage waveform is the integral of or integration of input voltage waveform is known as integrator or integration amplifier. So op-amp integrator can be used in various applications, commonly used in various applications like analog to digital converters. Integrator is used. In signal wave shaping circuits, integrator circuit is used. Integrator circuit is used for waveform generation in waveform generators. Now this figure shows the circuit diagram for basic integrator circuit implemented using operational amplifier. The input voltage signal that is to be integrated, for example, input is sine wave signal, it is applied to inverting input of operational amplifier through resistor R1. I1 is the current resulting due to input voltage Vin, and the current flowing inside operational amplifier IB is the input bias current. This basic integrated circuit using operational amplifier can be implemented using basic inverting amplifier with feedback or closed loop inverting amplifier. In place of feedback resistor RF, feedback capacitor CF is connected and output is taken across the feedback capacitor CF with respect to ground. So the current flowing inside operational amplifier is the input bias current IB. The inverting input of operational amplifier, that is at point V2, it is acting as a virtual ground, and non-inverting input is connected to ground. So inverting input of operational amplifier, it behaves like a virtual ground. And load resistor RL is connected at the output of operational amplifier. So voltage appearing across RL is nothing but voltage coming across a feedback capacitor CF. So feedback capacitor CF, it is acting as an integrating capacitor. So voltage across feedback capacitor accumulates or integrates with respect to time for a given input voltage signal. Now let us derive the expression for output voltage of op-amp integrator. So apply KVL at node V2. So current flowing towards inverting input at node V2, I1 equal to, so that current splits into two parts. The current, a part of current flowing through feedback resistor RF, that is IF, and current flowing inside the inverting input of operational amplifier, that is the input bias current IB. Let this is equation number 1. Since input resistance of operational amplifier, which is ideally infinite, practically it is very large resistance. So current entering inside operational amplifier, that is the input bias current IB, it is very, very small. So neglecting input bias current IB, current resulting due to input voltage signal, that is I1, is approximately equal to the current flowing through feedback capacitor CF, or current flowing towards feedback capacitor CF. So current through and voltage across capacitor is given by current flowing towards capacitor IC equal to, say, into a derivative of capacitor voltage with respect to time, derivative of Vc with respect to dt. So let us substitute the value of current in terms of voltage and resistance. So Vin minus V2 upon R1. For I1 we can write Vin minus V2 upon R1. So that is equal to, for IF we can write current flowing towards capacitor CF into derivative of V2 minus VO. But the voltage at non-inverting input is 0 volt. So voltage at inverting input is V2 is also a 0 volt. Since open loop gain, basic internal gain of operational amplifier is very large, ideally infinite. So op-amp tries to equalize voltage at inverting and non-inverting. As voltage at non-inverting is 0 volt, so voltage at inverting input, that is acting as a virtual ground, is also 0 volt. So we can simplify above expression, Vin upon R1 equal to Cf into derivative of minus Vo with respect to time. Let this is the equation number 2. Now integrating both sides of equation number 2 with respect to time, integration of Vin upon R1 with respect to time for a time interval 0 to t second equal to the integration of Cf into derivative of minus Vo upon dt into dt for a integration time interval 0 to t second. So after simplification, we are getting Cf into minus Vo plus Vo at time t equal to 0 second. So after simplification, the final equation for output voltage of integrator Vo equal to minus 1 upon R1 Cf integration of input voltage Vin with respect to time for time interval 0 to t second plus C, where C is a constant of integration constant. It is proportional to the value of output voltage at time t equal to 0 second. And the equation number 3, this is equation number 3. So equation number 3 indicates that the output voltage of op-amp integrator is directly proportional to negative integral of input voltage signal Vin, and output voltage is inversely proportional to the time constant R1 Cf. Now this figure shows the waveforms for the input voltage signal and output voltage signal, considering two types of input signals. When input given for op-amp integrator is a square wave voltage signal, in that case the output voltage signal will be triangular wave. So output is with a negative sign with respect to input signal, and if input is sine wave signal, input is sinusoidal voltage signal for op-amp integrator, then in that case the output voltage waveform will be cosine wave signal. So integration of sine is a cosine, so output will be cosine wave voltage signal. So for a time interval, the input voltage is integrated at the output. Now when input voltage Vin equal to 0 volt, the integrated circuit acts as open loop inverting amplifier for input offset voltage VIO, and feedback capacitor CF acts as an open circuit. Its reactance tends to infinity. So input offset voltage VIO and a part of input bias current charges feedback capacitor CF and produces error voltage at the output of integrator circuit. So to reduce unwanted error voltage at the output of integrator, we can add a feedback resistor RF parallel to feedback capacitor CF. So that is what practical integrator circuit. So this figure shows a circuit diagram for practical integrator circuit. Feedback resistor RF is connected in parallel to or across feedback capacitor CF to reduce unwanted error voltage at the output of integrator, as well as to limit the low frequency gain and to minimize a variation in the output voltage. So RF is connected across CF to correct gain roll-off rate and correct circuit stability problem and reduce error voltage at the output of integrator. So additional feedback resistor RF is connected across a feedback capacitor CF. So this is what a practical integrator circuit. Now this figure shows a frequency response of a basic integrator and a practical integrator circuit. So figure shows a graph of gain versus input signal frequency. So there are two graphs. The one graph is for basic integrated circuit. Now another graph is for a practical integrated circuit. So it is a graph of gain versus frequency f, where f is some relative frequency. So there are two frequencies, frequency Fa and Fb. The frequency Fa is a gain limiting frequency. From frequency f to Fa, the gain remains approximately constant and it is given by Rf upon R1. So after frequency Fa, the gain decreases at a constant rate of 20 dB per decade up to frequency Fb. So frequency Fb is a frequency at which gain is 0 dB. That is a closed loop gain of op-amp integrator AF equal to 1, numerical value equal to 1. So in between frequency Fa and Fb, the op-amp integrator circuit acts as an integrator and integrates input voltage signal. So Fb is a frequency at which gain is 0 dB and is given by Fb equal to 1 upon 2 pi R1 Cf. The gain limiting frequency Fa is given by, designated as Fa, is given by 1 upon 2 pi Rf Cf. So R1 Cf and Rf Cf values should be selected such that Fa should be less than Fb for proper integration of input voltage signal. For proper working of integrator, the frequency Fa should be less than Fb and value of Fa equal to 1/10 of frequency Fb. So therefore, value of feedback resistor Rf equal to 10 times of input resistor R1. So proper integration of input voltage signal, the time period of input signal must be greater than or equal to RFCF, time constant RFCF, where RFCF is equal to 1 upon 2 pi Fa. Now a student can pause video here and think over this question and try to answer this question. What is the range of input signal frequency for which output is integration of input signal? So after a frequency Fa, the gain decreases at a constant rate of 20 dB per decade. From frequency F to Fa, the gain remains constant, that is given by Rf upon R1, and after Fa, frequency Fa, that is the gain limiting frequency, the circuit works as an integrator and the gain of circuit decreases at a constant rate of 20 dB per decade. So therefore, between frequency Fa to Fb, output is integration of input voltage signal and circuit acts as integrator. So this is a reference for this session. Thank you.